What I want to do is start here. We didn't really talk about this little chart that we didn't quite, this was like at the very end of our last day. I didn't make a big deal about this because essentially this is what we've been doing the whole time. You guys remember basically anytime we've talked about any sort of series, I've said, hey, does the nth term test tell us anything? What about the geometric series? And so all this is, and I'm kind of zoomed out for a reason because it's in front of you and we're not going to talk about it a lot because we've already been talking about it. But it's basically just a flow chart to help you organize your thinking. So what I'm hoping is in your brain, when you encounter some series and you're thinking to yourself, is converge or diverge, I'm hoping that this structure is already kind of built into your brain because we've been using it. But this is it just down on paper if you'd like to see a visual to help you remember it a little bit better. There it is. So does that make sense? Does this seem familiar? Remember how we've gone through every step just about every single time? This is just a visual for you, and it's there in your packet. So like I said, we're coming full circle today, and we're going to come back around to that thing we did on day one, and it's right here. And by the way, can you guys see how it says intro video begins at the top? You see that? So you guys have done so well, and we've moved quickly enough. We're just going to go ahead and do the intro video together, because the intro video really wasn't even scheduled. So when you see intro video assignment for this coming up, you don't need to do it yet, because it's for tomorrow. We're going to cover all this material easily within our class.
Wait, so the Taylor, we're talking about the Taylor series?
Yeah, the Taylor intro. Yeah, we'll just do that right now. So you don't need to do that. You can choose to tell Santi, and I guess Julie will find out here in a little bit. You can choose to tell Santi that or not. It's up to you. You want him to just watch it again.
You have to watch it 3 times actually.
And I'm recording this right now so he can hear your decision when he watches this video. Anyhow, so the polynomial that we found on day one, we technically found what's called a Maclaurin polynomial. So there are 2 different versions of these polynomials. Are really the same thing. You're going to see here in a second. One of them is called the Taylor polynomial, named after a man from way back named Brooke Taylor, who was credited with this. And then there's another guy from Scotland, last name Maclaurin, who is credited with this other version of this. And if you look there at the bottom of that little set, I say compare the Taylor and Maclaurin formulas. What similarities and differences do you see? So let's start there. What do you see as you compare all those terms in that little formula there? What do you see that's the same? What do you see that's a little different?
You just keep taking the integral.
Say one more time.
It looks like you're taking the integral of f prime. Or sorry, derivative, yeah.
Yeah, progressively from well, I didn't know if you were talking about from right to left or left to right, but yeah, from left to right, we're increasing our derivative degree by 1 each time. I agree. So I'll just put here, our derivatives from left to right, we're doing the derivative. Okay, so you can see that in there. From left to right, we're doing derivatives. What else do you see that's the same or different? Yeah.
You're dividing the polynomial by the factorial of the degree of the derivative.
Yeah, there we go. Good.
Yeah.
You said that well. So I'll put division by degree factorial. Is that a good way of interpreting what Logan said? Yeah. Dividing by the degree factorial. Okay, so those are some similarities, and I think those are excellent similarities. Does anybody see any differences?
That x minus a constant.
Yeah, x minus a constant, and that goes with the Taylor, right? Okay, so Taylor is x minus c. But then what about the Maclaurin? What does the Maclaurin have?
Just x.
It's just an x. So would it be fair to say that, and I'll erase this all here in a second, would it be fair to say that Maclaurin is x minus 0?
Yes.
Yeah.
Right? Because x would be the same thing as just x minus 0. And that's really, if you want to boil it down to what the difference between these two things, if you want to boil it down to the difference here, that's it. Like you could say it this way. There is no difference at all other than what we call the centering point. So notice back up here at the top, it says the formula for the Taylor polynomial centered at x equals c. So that means c could just about be anything you want. It could be 0, or it could be 1,000, or it could be 1, or it could be 1/4. That c could be any constant where we choose to center our polynomial. Centering being where we start, where all, and there's a little more to it than just that, but for now we'll just think of it as where we start everything. Whereas the Maclaurin polynomial doesn't say anything about at x equals c, there's just no notation about that. So for Maclaurin, what do you think the c value is?
0.
Yeah, it's at x equals 0, our centering point there. So you could say that a Maclaurin polynomial is simply a Taylor polynomial centered at 0. So they are genuinely the same thing. It's just the Maclaurin is specifically at 0, whereas the Taylor polynomial could be any particular centering value we choose, or perhaps chosen for us. That make sense? Okay. So what I want to do, excuse me, is I want to build one of these out. We're going to do number 1, and then I also want to, you can see there, I want to look at the graph of this as well. And so let's see here. Let's do this. I'm going to scooch this a little bit, maybe something like that. So number 1 says find the first 4 non-zero terms for Maclaurin polynomial for g of x. And can you guys see how I've got the graph for g of x over there? I just called it y, but you can see the same thing, right? Okay. So think back to day 1 when we first started doing this. I want you guys to think about the way we match things. Remember how we did the error? We subtracted, and I had you guys kind of guess. Maybe the next term would be this. And it only took like 2 or 3 terms. And you guys had the exponents down, right? You're like, okay, it's x to the first, x to the third, x to the fifth. And it took a little while to guess the factorials. Who was the good guesser? I forgot. Who was the one that eventually guessed? Probably Aiden. Was it you, Aiden? I don't remember. It doesn't really matter. I was just kind of curious. We started to get some guesses. We got some good guesses. We saw the pattern. And by the time class was over, we had done like 3 of them. And you guys were like, oh, okay, I think I get this. Let's go a little bit deeper, though. Let's look at the Maclaurin pattern here. And we're going to just take this term by term. I'll do it like this. So let's just start here. I'm going to write my Maclaurin polynomial right here. I'm going to say p of x equals, and I want to analyze this first piece. So I'll draw an arrow to it. The first piece, the first term is f of 0. So if I said, graphically speaking, what does f of 0 mean? What would you say? It's where x equals 0, but what's f of 0?
Y 0.
It's not when y is 0. Say again?
F of 0 is 0.
F of 0 is...
Equals 0.
Okay, now you're getting too specific. I'm just talking about in general. Like if I say
So is it y of 0?
it's the value of the function at 0, but on a graph it's the y value, right?
Y value.
It's simply the y value for f when x is 0. So when I see f of 0, aren't I essentially matching my polynomial with the y value of my curve? I'm making sure that the y value at 0 matches. So let's talk about this. All I got to do is plug in a 0, right? So you said it, ln of 1, which is? Oh, this is the hard question. It's 0, right? E to what power is 1? It's 0. Okay, so my first term is 0. And notice the way the instructions are worded here. It says find the first 4 non-zero terms. So I found the first term technically is 0, but I want to know the first 4 non-zero terms. So I for sure got to keep going. Technically, I haven't even really found a term yet, at least not for the instructions. So then the next term is f prime of 0. So in order to figure that out, I need to find f prime of x. So I'm just going to come down here and I'll just make some notes to myself to show some work here. What's f prime of x? That's right. So then we can do this in our head. What's f prime, bless you, of 0? Okay, so we have our first non-zero term. I would say plus 1x. I want to point something out. This is a really great connection. I hope that you'll be able to grasp this. If I stopped right there, I'm not going to, but if I did, what kind of a thing is p of x equals 0 plus 1x?
It's a line.
It's a line. And wouldn't that, I'm just going to sketch this in, wouldn't that line look about like that? And what would we call that line? A tangent line, right? So you have actually found Taylor and Maclaurin polynomials before, but we always stopped at the first degree and called it a tangent line.
Oh, Miss Ray.
Get it? You get it?
You be doing this like that.
I don't want to. Why are you doing this to us?
I'm trying to help you see connections instead of just memorizing junk.
I don't want to learn the next thing.
That was terrible.
I want to see.
Okay, so
Just don't wanna take
I
it.
love your attitude, Meg. It's sterling. So here's what I want you guys to think about. We found tangent lines over and over and over again, right? To the point where you could probably do it in your sleep, right? Or semi-awake, maybe?
I have to keep on learning. You severely overestimate my abilities.
Wasn't that better than like thinking that you're worse than you are?
No, I don't.
Okay. So anyhow, so here's what I want you to think about. We've been able to match this tangent line essentially with our curve here. We are going to take it a step further, and we're going to say, well, let me put it like this. At this point, haven't we matched the y value and the slope at that particular centering point? What if we wanted to match the concavity? What if we want to match the concavity? What would we need to use? The second derivative. We need the second derivatives to match. So look what that, so there's the first term, there's the second term, and what does the third term involve?
There's factorial in there.
Well, but what derivative does the third term involve?
That's the second derivative.
And that might help us match the concavity, right? So I'll come down here and I'll say f double prime equals, so f double prime would be what? Negative x plus 1 to the negative 2?
Oh, shoot, I could have just done
Did I do that right?
Who did the quotient rule?
You could do the quotient rule, for sure.
If you really did the question, that's
Yeah, that's just, I don't even know how you read.
So then we plug in a 0, and when you plug in a 0, what do you get?
-1.
Negative 1. So according again to the Maclaurin structure up there for this term right here, I'm going to write minus 1x squared over 2 factorial. You see how I'm just like, I'm basically plugging in pieces where they go, but I want you to understand the graphical piece of it is I'm matching the y value, then I'm matching the slope, now I'm matching the second derivative. What do you think would come next in a pattern like this?
Third derivative.
Let's match the third derivative. And you might think you see the pattern, but let's make sure you actually do. So third derivative would be, what, 2x plus 1 to the negative third. There, of course, there's a chain rule factor of 1 on all those. I'm just not writing that. So now when you plug in a 0 to get to that next term, when I plug in a 0 and find f triple prime of 0, what do I get?
2.
Just a 2, right? It's basically 2 times 1.
Yeah.
So it'd be plus 2x cubed over 3 factorial. And then that little note over there about the f with the n in parentheses stands for the nth derivative. So for us, I think our last term is going to end up being the fourth derivative. So I'll write
Casual fourth derivative.
f parentheses 4 of x. Right? That, instead of writing 4 little tick marks, we just write the parentheses 4. It's not to the fourth, right? It's the fourth derivative of f. So this would be what? Negative 6 x plus 1, yeah, to the negative fourth. So then when you evaluate this at our centering point, which is 0, we get negative 6. Okay. So minus 6 x to the fourth over 4 factorial. Okay, so at this point I've got my first 4 non-zero terms for my Maclaurin polynomial, which we know by definition is centered at 0. And that's what it's supposed to be. So what I want to do is not rely totally on my memory. I'm going to write this down real quick. I'm going to say P equals x minus x squared over 2 factorial plus 2x cubed over 3 factorial minus 6x to the fourth over 4 factorial. And I want to do a little bit of graphing here and take you through this pattern of graphs. So I'm going to erase this, and I want to come over here on my graph, and I want you to notice the various stages of evolution of our polynomial and how it changes over time. So if I just put the first term, I'll put y equals, the first term was just 0. So I get that lovely green line. So do you see how at the centering point, our red curve and our what now is a green line, at the centering point, they perfectly match, right? But the minute you move off that centering point, which of course is x equals 0, they don't match at all. It's not even close, right? So then we thought, well, let's match up our first derivative. That's where we went plus x. There's that tangent line that I showed you, where you got a little upset with me about making you make connections between things, right? So there's this, and of course now the y value matches at the centering point. I almost call it the point of tangent z, which is really what it is, right? So the y value matches and the slope matches. But then once you move off that centering point, nothing else matches very well, right? Okay. So then we added another term, and the next term was minus x squared over 2 factorial. And so now, if I click off this, can you see how now not only does the y value seem to match, the slope seems to match. Now the concavity is starting to be about the right match as well. Notice how our interval of convergence, remember that thing we talked about on day one? It's starting to widen out a little bit too. For a while there was just like 1 point. And now it appears like it might be widening out, or at least visually getting a lot better. And then we did what that third term was, plus 2x cubed. And what's 3 factorial?
6.
So there's that. Okay, so it's seeming to match. I mean, that one, since the tails go the wrong way, seemingly, that one maybe doesn't seem to improve it all that much. I had the fourth term on there, which was minus 6x to the fourth. And then, 4 factorial is 24. Okay, so now you can see maybe that interval of convergence is widening out even a little bit more. It's a slow process for sure with this one. With others, remember when we did with sine, that interval of convergence seemed to jump from here to here to here to here. And didn't, by the end of class, didn't we almost have it all the way up to the outer edges? I think it was close, pretty close. What you're going to find with these is that depending on the type of polynomial, later on we'll call it power series, that interval of convergence will either grow really fast or really slow, or sometimes it'll be completely limited. It won't get very large at all. But we can see how the more terms we add here, the more it seems to be. I mean, this over here really bugs me. You know, like when you look at this right here, this tail, you can say, hey, it looks like it's sort of bending towards the red graph a little bit. But then this is what really bugs me here, right? Because the green graph just drops right off the bottom. Doesn't seem to match at all. The question would be, if we did some more analysis, basically would this point creep out there a little further? Would it widen out more and more and more? Maybe it would, maybe it wouldn't. We could do some analysis and actually figure that out. That's a topic for another day. Right now we're just working on building these. Does that make sense? So you can always turn to a graph with these. We're not going to do that with all of them because it's just too time intensive, but you can always turn to a graph. I thought maybe a good next step now would be to go back to a familiar friend, number 2. Didn't we do a power series for cosine on day 1? So let's see if you can, and it wants a Maclaurin polynomial, and it wants the 6th degree. So I kind of varied what I asked for. So in number 1, I said first 4 non-zero terms. Here I'm just concerned about degree. Most of the time it's going to be first 4 non-zeros. Most of the time, but sometimes it'll say degree. So let's see if you guys can do number 2. We're going to be doing Maclaurin again, so centered at 0. See if you guys can work together or by yourselves on that. And I'll check your answers and see if we need to supply Santi and Julia with any additional info. Good love to talk. Are you already done with this one? Stop thinking about abortion. Do the simple stuff like calculus.
Oh, yeah.
Abortion is bad.
Well, not if we do this already. No.
That's not true at all.
The article is definitely
The article
pro-life.
is
completely pro-life. What?
It reiterated the same line every time.
It's absolutely that.
It was very
Yeah, let's start this debate in math.
So your first step would be to find f of 0, right? Find f of 0.
negative sign of
Oh.
So Nick is already on to, it should be negative sign of 0, right?
Yeah.
Because you're centering point 0.
Yeah.
Yeah, so did y'all get your first term being 1?
Yes.
Nice.
At least
It
it
starts.
starts.
So if you wanted to get a look at the graph here, for those of you that have the first term being 1, what have you found?
Just starting altogether.
Yeah, okay, so you found like, you matched the y value, but what is the black line?
Tangent.
It's a tangent line, right?
Oh.
You found that you congratulations, you found the tangent line to cosine
Fun?
at x equals 0, but we gotta go all the way to 6th degree. So I think I mentioned this before, when we find these Taylor and Maclaurin polynomials, we're really finding, you could call them like tangent curves, right? Instead of just a tangent line, we're taking a tangent line and extending it to be, what if we made it curvy? What do you guys get for your first degree term?
0.
Should be 0, right? Because that derivative would be negative sine of 0,
Happens.
which happens to just be 0, right? So
What's negative 0?
any chance, does anybody have a second degree term?
What if it's over 2 factorial? Or negative?
You say negative 1x over 2 factorial. Did I get that right?
That's what I.
That's not right. It's x squared.
X squared we're going with? Okay.
Oh,
Let's see if that changes anything. Oops.
And that's on polynomial.
yeah.
Well, it's interesting, yeah, with the squared in there, this seems to be a lot better, doesn't it? So at this point, you guys have matched the y value, and you've matched the slope. The slope, of course, is 0. And by this point here, you've matched the concavity. That purple graph, the black graph is looking a lot better now, at least on the part that I'm zoomed in on. Has anybody figured out what the third degree?
Zero.
So basically on all the odd,
It's all the even ones.
hey, listen now, basically on all of the odd degrees, isn't your derivative sine in some form or another? And what's the sign of 0? So you can think every single odd term should go to 0 with this Maclaurin polynomial. Yeah. Okay, so so if there's no third degree, then maybe there's a fourth degree. Anybody know what the fourth degree is? And is it a positive x to the fourth or a negative? Positive? Okay, good. So plus x to the fourth over 4 factorial. Okay. Basically, aren't all your derivatives either going to be 0 or plus or minus 1? Because it's either going to be the sine of 0 or the cosine of 0 with, positives and negatives thrown there as well.
I'm just waiting for something to happen.
No, this is it. Basically, if you can make this,
I don't trust you.
are you talking about just for this one or in general? Like as we move forward, I think the next one is going to be a Taylor, or one of the ones coming up is a Taylor centered not at 0. So that'll be a little bit different. It will be.
Maybe
But
I'll wait till I see
the
that.
pattern is the pattern. It really is. So does anybody have the final? What will be our final one? Because we have to go to 6th degree.
Minus
Minus.
x to the 6th over 720.
I'm just going to 6 factorial And look at that, I'm pretty zoomed in, but you can see that interval of convergence has widened out fairly quickly. Probably another term or two, and I would have it would look like the black graph and the purple graph have coincided almost perfectly, right? Very, very close. Okay. So what we have up there, welcome Julia. What we have up there is our, we have our Maclaurin for cosine at 0. What do you guys think?
Yeah.
All right. So number 3 is the most familiar of friends for you.
Wait, are we approximating the value?
Oh, sorry. Yeah, I forgot the last part. So with that right there, what you would do to approximate cosine of 0.1, you would just go cosine of 0.1 is approximately, and then you're just going to be plugging in a 0.1 for all your x's, right? Polynomials are very easy to handle. That's one of the reasons we do this, of course. So it'd be 1 minus 0.1 squared over 2 factorial plus 0.1 to the 4th over 4 factorial minus 0.1 to the 6th. Obviously, it's a little bit laborious. But can you see how someone could use this in a programming application to make the computing so much easier, right? Because polynomials are really easy to handle versus something like cosine or sine would be a little harder to actually code, right? It's easy to code polynomials. Okay. And then, of course, on your calculator, you could figure this out. You could actually do it by hand, too, right? It wouldn't take forever, but either way. Number 3 is the most familiar because that's the one I started off the very first day of the unit. I tried to fool you with number 3. So if you would, let's go back and see if you can find this. Notice the wording has changed a little bit. Notice it says, find the 5th degree Taylor centered at 0.
So it's just a Maclaurin.
So it's just a Maclaurin, right? I could have written it either way. I chose to write it like this for whatever reason.
It's a nice car.
So like we get one,
I like every question from the player.
every 5.
So please try number 3.
But you have to get 5 in a row.
Please try number 3. Julia? I don't know. You're going to have to lean on.
She's
So you're so caught up. Oh my gosh.
In fact, she's on probably with us
So the timing could not have been more perfect.
Yeah.
Well done. So we're on number 3. It's
I
like you've
didn't
been-
know that we were going to be doing that today, but I saw that it was due tomorrow and I didn't have time to do it tonight.
And I just got done
Last
telling
night.
them, maybe Meg told you, like, hey, we're just going to not do the intro.
I just
because
saw
we have
that.
time to do
Yeah,
it, so
so,
it's perfect.
I know, very good. So it worked out.
Julia. Awesome. Anyways, so yeah, we're doing number 3, finding 5th degree. We'll eventually take a trip down memory lane from day 1. I'm going to encourage you guys all to talk, peek, see if you're doing the same thing as your neighbor. Like what you're doing there, Justin. Set up. Smart. I'm just noticing different strategies here. Some people are setting up the structure, others are jumping in and doing kind of a list of derivatives right away. You can make this work in a number of ways. No, typically not. I mean, do you remember, so, you remember when we did the ratio test and how we kind of like split up parts of the factorial so we could cancel? That skill could come in useful, where you just say, they would be saying something like 5 factorial is really 5 times 4 factorial to allow you to do some canceling of some kind. But otherwise, I'm not going to say, oh, come on, let's do 9 factorial real quick. Yeah, what's the point?
Yeah.
Okay, so let's see how you did, or how you're doing, I guess. What did you guys get for the very, very first term? 0, right? Because sine of 0 is 0. What did you guys get for the first non-zero term?
X.
Okay, so the first so double check everybody, look at your paper. Other than potentially the zero you had at the start, was your first non-zero term 1x. So just to remind you, essentially what do we have at this point? What's the red graph? It's a tangent line, right? Thing we've done a bunch of, but now we're going to say maybe we can make this better. Maybe we can make it a tangent curve. What did you guys get for your second degree term? 0, right? Because we're back to saying sine of 0 for our coefficient. So then your third degree term probably showed up. What did you get for that?
Minus x cubed over 3 factorial.
Yep. And that's that number you guys came up with on that day one where we were all over the place. Somebody eventually said, let's try 5, let's try 6. 6 ended up being the right number. You can see that interval of convergence has spread quite a bit. You guys good? Okay. What you guys get for your fourth degree? 0 again. So you're noticing for sine, all of the even degrees head towards 0 for a Maclaurin. Again, cool pattern. So then your fifth degree must have shown up, and it's probably plus, wasn't it? And x to the fifth over 5 factorial. So, and we get there, and of course we could keep adding more and more terms. This said stop at fifth degree, so that's where I'm stopping. What do y'all think? Getting comfortable? No big scary thing yet?
Not yet.
Okay, not yet.
It's
All right.
coming.
You think it's coming. All right, so
Feels it in the bones, guys.
so here we go. Number 4. Number 4 could be the big scary thing. Let's find out.
There
Looks
it
like
is.
it.
Oh, there it is.
I said could. We'll see what you think about this.
Okay, well,
Um,
it has a pi in there.
hard, but it's just gonna suck.
Mr. Anderson, I don't know my unit circle.
Come on, you know this. This is a special trust.
Just use the special triangles. I like Nick's
Look at
idea.
it And use your phone and like take a picture of it with your
That's
photograph
not
in
how
hand.
things work, Sam.
Okay, so guys, here we go. Whoops, that's not what I want.
I don't just like.
Hey guys, I want to shift modes a little bit. I want to give you a little more direct instruction on this one. So this number 4 is called a third degree Taylor polynomial. And as you all noticed, it's not centered at 0 like the previous one. It's centered at pi over 6. Okay? Guys, you ready? Here we go. So I'm going to I'll put p, I'll put p sub 3 of x equals. So my first term is simply going to be f of pi over 6. So as long as we can do sine of pi over 6, this would be a no calculator activity. I do not want decimals here. Decimals are ugly, nasty things. So what's sine of pi over 6?
Wait a minute.
0.5. 1/2.
1/2, yeah.
Wait.
Wait, it'll get ugly later on. So 1/2.
Oh no.
So there's my 0th degree term, right? Plus, well, I don't know about plus. Yeah, it is going to be plus. I normally wouldn't put that in there yet. Now I've got to do f prime of x. So the derivatives all here should be pretty easy. What's f prime of x? Cosine of x. And therefore we need f prime of pi over 6. So cosine of pi over 6.
Root 3 over 2. It's
Okay.
ugly already.
So here is your next term. It's root 3 over 2 times x minus pi over 6 to the first. So now listen. This is where the polynomial, ladies, listen. This is where polynomials, again, show kind of like the nice side of this. You guys remember how we shifted parabolas and cubics and cosines and sines? Remember how it was like if we wanted to shift right, it would be x minus something. If we wanted to shift left, it would be x plus something. That's what's going on here. We shifted the whole thing over to pi over 6 to the right. Therefore, it's x minus pi over 6. So all those polynomial properties you learned back in Algebra 2, they still apply. Okay, so to get so that's our first degree term. We only need third degree term here, so we only have 2 more to go, right? So f double prime of x is what we need next. That's, of course, negative sine of x. What is then f double prime of pi over 6? It's negative 1/2, right?
That's what I was about to
So it's
say.
going to be minus 1/2 x minus pi over 6 squared over 2 factorial.
test on it soon, so you better find a way to enjoy it.
When's the test? Wow.
Last one would be based on the third derivative. So f triple prime of x equals what? Negative cosine, yep. So then what is f triple prime of pi over 6?
Negative root 3 over 2.
Got it. So negative root 3 over 2 times x minus pi over 6 cubed over 3 factorial. And how do I know that I'm done?
Because that's the third degree.
Correct. Okay. So I think I do want to look at a graph for this one and just kind of see what the graph does. So y'all have this written down. You can help me out because I don't have it memorized. You guys with me? Okay. So it's going to go away. And let's look at kind of the evolution of this as we go. So I'll say P of x equals, I remember my first term was 1/2. Okay. So what does this mean? Well, I would say pi over 6 is just a little bit more than 1/2, is it not? You with me?
Yeah.
So I would say that that is right there. There's my centering point. So can you see how the y values match for the line and the curve? Okay. So I need to do a little bit better than that, of course. So it's not just 1/2. It was, the next term was what, plus, what, square root of 3 over 2
Yeah.
times x. No, x minus pi over 6. Almost forgot. Okay.
It's still sine of x, it's not
Oops.
sine
Sorry?
of, f of x is sine of x, not sine of x minus pi over 6. Your original function.
Yeah, that's okay. I'm not shifting sign anywhere. I want to build a Taylor polynomial for sine, but I don't want to center it at 0. I want to center it over at pi over 6. So I'm not shifting sign anywhere. Sign is where it is. I'm just changing my centering point from 0, which we did a few minutes ago, to pi over 6. Make sense?
Yes.
Okay. All right. Then it was, what, minus 1/2? X minus pi over 6. Oops. Squared, you said. And then over, yep, 2 factorial. Yikes, right? And then you can see what that graph's doing off to the side. And finally it was it minus again?
Yep.
Minus
Root 3 over 2.
root 3 over 2 times x minus pi over 6. Yeah, I always do the same thing. Cubed over 3 factorial. So you can see it's getting better, isn't it? You can also see that that centering point is still where it is. You can, for some reason, Desmos leaves that little gray point there. That's still our centering point right there. Right? So I centered it at pi over 6 instead of centering it at 0. And the truth is, I could center this wherever I want to. It would change all the derivatives. So I could center this at like 5. So they would all be x minus 5s, right? But then your derivatives would change to accommodate that as well. You'd have to build that. You'd have to construct an original version. Okay. Let me say this. See if this makes sense to you. So I would say that my blue graph up there, that's my polynomial, right? My blue graph at this centering point, my blue graph perfectly represents the purple graph at the centering point. It's the same in every way. But the moment you move off of that centering point, you can't really see it here. Maybe we'll play around with this in a second. The moment you move off that centering point, the purple graph and the blue graph will start to disagree. Not by very much, but they will start to disagree. So let's look and see how close, this could be interesting. See how close we have to get to start to see that. So they seem to agree. I'm going to zoom in here on my centering point. Boy, they look like they're the same, don't they? Let's keep going. You can see the scale down there. Centering point is like right in there between like 0.5 and 0.52, probably somewhere in there. I keep zooming in. Man, they look really close, don't they? It's going to be really hard. See, when I'm around that centering point, they are almost the same. In fact, yeah, look at that. It's hard to see. It might be impossible to see. Let's see how far Desmos will go. Oh, you see it now? So I'm at, you can see the scale down there. I'm like right around 0.5, and they're off. If I start strolling over, they should start to get a little bit closer because I think pi over 6 is to the right of us. Oops. I don't know. Visually, can you see it? They're getting a little closer, aren't they?
Yeah.
So somewhere over there, they would eventually meet. But I'm off the centering point. Let me zoom back out. Do you see it? As soon as I move off the centering point, they disagree. So one of the things that we will do is we will do a lot of error analysis and do a lot of talking about how to quantify that error, right? So my point with that is just to say, at the centering point, they perfectly are the same. There's no difference. As soon as you move off the centering point, and did you see how far I had to scroll or zoom in to get there? That means they're like really, really close, but they are different. So we will do some error analysis on just how different they are coming up. One of which is, you guys remember the alternating series error bound? Alternating series error is bounded by what?
The previous.
Not previous.
The next term?
The next one, the first neglected term. That'll bound our error for those. For others, it's something different. So this number 5 is going to be a really good place for us to finish. So number 5 is very different. Can you see how building a Taylor series like what we just did potentially is quite time consuming?
Yes.
So it's not like you're going to see like, hey, let's do 20 of those. You have 10 minutes. Go. Number 5 is a nice way to see if you understand how a Taylor series or Maclaurin series is built without making you build it. And by the way, for number 5, can you guys tell what kind of polynomial number 5 is? Is it Taylor or Maclaurin?
It's Maclaurin.
Why?
Because the centering point is 0.
How do you know centering point 0?
Because x is minus 0.
Yeah, there's no x minus something other than 0, right? It just x is, you know it's Maclaurin, which actually goes nicely with the question. We can go a little bit deeper with that here in a second. But if you would, see if you can figure it out. I know it's a little bit off the wall. See if you can do number 5. This will put us in a nice place. Yeah.
No, it says that are the first 3 times.
Oh.
Good. So first 3 terms are given there for g of x. What is the value of g double prime of? Okay, give you a few minutes. Look it over.
But the G prime will be over 2. Or G double prime will be over 2. So it's just 1.
Come with an answer yet? So g double prime would definitely be related to that.
Just so write it up, you know that the first term is G of 0, that's plus G prime.
Double prime over
Times that.
G double prime
Your handwriting is so nice.
Right. Yeah, of the second degree term. Yeah, exactly. But the 5 doesn't match what it should be,
So
right?
then
Isn't the denominator 2 factorial?
It's G double prime
So
is 0
5
times
makes,
x
so make if the denominator on that was a 2,
times x squared over
right, 2 factorial, then I would completely agree and say we're done. But the fact that that's a 5,
I am not looking forward to this discussion, Hayden.
Yeah, me
I think
either.
there's a little bit of work you could show here.
You guys see your Bible, guys?
6/5.
That would hopefully help you.
What? You don't want to see your Bible?
Go back and look, go back and compare this, this stuff.
I'm not really worried about our class though, it's a fairly tame class.
I wasn't really worried about
Just
that. I
some
wasn't worried about
so
our
you can get a
class.
little
Yeah, but she's
equation
gonna be
going.
fine though.
That's what I'll show you guys
Yeah.
after dinner too.
But she said if someone comes after, she's gonna throw some bows.
Actually, who?
To Cheddar.
Actually, she.
So you have one? No, you're on your way.
I'm working on it.
You've got an answer. You have an answer?
Yes.
You have an answer?
I haven't changed my
Yes,
answer.
I'm sure.
I changed my solution.
Okay.
That sounded kind of fun.
You did that.
Sure.
not bad.
Watch. No, I know it.
I don't.
Which Ashley? I didn't hear you.
To Shutter.
What's she do?
I don't know if she does much of anything.
Yeah, I don't know what she does.
That's,
I know she used to play soccer,
She has
but
blonde.
Remember, I'm recording this, so anybody could listen to this.
that's called tape.
No.
Well, she's
I'm
more
just saying.
What
I
is
heard-
she? I'm not quite sure. I knew she used to play soccer.
I caught the end of that conversation. Heard something about somebody throwing elbows,
No,
and then
we're
you
talking
saying
about
they don't do
Debate.
anything.
Our debate in Bible.
Discussion,
Discussion.
friendly conversation. There we go.
Dude, our class didn't.
Friendly, heated conversation about abortion.
I heard
Most
that.
words don't go together.
what class
Friendly.
was it?
Typically not. Yes.
Peter literally stopped the discussion
God.
and like called out.
Oh, so I didn't know what he was saying.
Cause
He said that good.
How did you hear about?
well, they're in the same class.
Oh, yeah.
No, they're not. Yeah.
Yeah, it's okay.
It was like I was just like.
That's what I-
So Caroline is in that class. and
Or you
she's
could just
telling me
divide by.
Hey guys.
Oh,
Hey, let's
that's what it is.
guys, if you wouldn't mind putting your nice conversation on hold for just a moment. Does this look familiar? What I just wrote up there.
Yes.
So here's what I would encourage you all to do. Take this and try to match it with your terms. So you can draw a pretty good connector between these two, right? That's just g of 0. So if I'd asked you what's g of 0, wouldn't you be able to say 7? Okay. And then these two go together. Hey, ladies. So those two to go together. And then wouldn't these last terms go together as well? What I'm really matching here is I'm looking at my degrees. So I'm looking at second degree. I'm matching those degrees up. And so then if those two things are the same, then wouldn't this 3/5 have to match this? So what I can do then is create an equation and say, all right, well, 3/5 has to equal g double prime of 0 over 2 factorial. And of course, once you write it like that, it's one step away, right? Just multiply both sides by 2, and you're done, so it'd be 6/5.
You're assuming that I can do simple.
I am assuming. Sometimes that doesn't work out that well, but most of the time it does. So my final point before you guys go is this. Notice I've written this symbol right here. Sometimes we're really casual with that symbol. You shouldn't be. When you write that symbol, you're saying that the thing on the left and the thing on the right have the exact same value. How do I know for sure? I want you to think about this. How do I know for sure that this is not some approximation, but this is an exact value?
Because it's at the center.
And at the centering point, yeah, the polynomial and in this case, whatever made this power series, or this polynomial, they're the same, right? At the centering point, the same. If I moved off the centering point, I would not be able to put equals. I'd have to put approximately something, and there would be an error involved. Hey, good news. If this is not 100% clicking for you, we're going to work on this again tomorrow, and we'll start to build in some of that error analysis in tomorrow and the next day. So appreciate you guys. Nice work.
are we just gonna use
See
the
ya.
big Lexington for this, or?
So for this one, no, because it's not an alternating. We'd have to use that thing I mentioned earlier called the Lagrange error bound.
Yeah.
Oh, yeah.
But that's-
Little Lagrange.
That'll be later on.